All right, good evening. You're welcome to today's class, Tutorials with From Eternity the Schoolboy. Today we are going to take a look at physics, and the topic for today, we want to start today, is measurements and units. Measurements and units. Now, there's something I want us to know, that in sciences, which physics is one of them, measurement is very, very what? Important. Measurement is very, very important. Because for anything to be measured, to be accepted in sciences, it must be duly what? Measured and proven to be what? Correct. Our reference book for today's class is New School Physics for Senior Secondary School by Professor M.W. Anyakoha, 2016 edition. This is our reference book for today's class and this topic. All right, let's continue. So measurement is not just, physics, pure sciences, physics and other pure sciences, they are exact science, because it's not just, most of the things we do, measurements need to be what? Exact. It's not assumption, because you need to be careful in whatever you are doing when it comes to what? Measurements. Now, what do you understand by the word measurements? What do you understand by the word measurements? When it comes to, when you want to interpret or explain the word measurement, it has to do with a kind of system of communicating a known natural phenomenon that has been properly studied and the quantity determined, communicating it to other scientists for proper understanding and to avoid ambiguity in handling that particular phenomenon. What I mean by this grammar blowing, what I mean is that when it comes to, as you are here now, you are in Nigeria, you take a measurement here. Maybe you know that the length of this is 1 meter. This length you measured here with the use of accepted units of measurement. Someone outside in other countries can still say, okay, still measure that same material you measured, and it gives the person the same what? Measurement. Do you understand what I'm saying? Okay, now let me use something else to explain this. Okay, let me go back to the scientific method we did. Now, when it comes to scientific method now, an observed phenomenon, natural phenomenon, lead to what? Hypothesis, right? Now, an hypothesis leads to what? Experimentation, right? To test the what? Hypothesis. Now, before you can say, okay, this is the quantity of whatever you are using in the experiment, you need to do what? Measure the what? Quantity. Am I communicating? Then, having measured the quantity of what you are using, Whatever you measured, you put it down that this is what I measured. Somebody outside, you publish your work. Somebody in other country, having seen your work, can also measure the same quantity of what you measured in Nigeria and carry out the same experiments where in their own country. If there is no system, an agreed system of measurement that say that from this to this is 1 meter, from this to this is the weight of this particular quantity is kilogram. If there is no such measurement, what it implies is that someone in another country will not be able to do what? Carry out the same experiment, because they may have an entirely different way of measuring their own thing, which may not even align with what you did in Nigeria. Now, this leads to what we call uniform, a system, an international system of measurements, so that whatever natural phenomenon that it is observed in a particular place can also be communicated to those in another environment, or be it another part of the world. Now, this measurement is not only used in sciences, even in our daily business transaction. You've gone to the market to buy rice, right? You went to the market to buy rice, even though that one, the measurement there is not that exact, because what they tell you that is cup here, what they tell you that is this is cup. You may go to another place, there will be change in the cup. True of us, because the cup is not calibrated. There's no standard. It's not standardized. There's no standard that this cup should have a capacity of so cm cube. Am I communicating? There's no, if most of the cup they use in the market here, do you see anything written on it? Good. And who calibrated it, you don't even know, because you may be here and say they call it cigar cup, right? Cigar cup. But the cup here, if you take the same cup and go to another woman, even in the same market, it may not be the same thing. True of us. Now, imagine in the world of science where you have such discrepancy. There will be trouble. True of us. There will be trouble. And how will you? Maybe you imported a kilogram of a drug or a kilogram of a chemical, and if there is no standard measurement, how will somebody else in another place be able to prove that this is also 1 kilogram? There must be a uniform, that the two parties understand that this is the uniform measurement we are going to use to be able to do get the same measurements. So measurement is very, very important, but if not, those in business will be cheated. True of us. Those in business will be cheated. And those in science, there will be errors. Can you imagine a scenario whereby someone is producing drugs, and different companies manufacturing different drug products, and there is no common system of measurement. There is no unified, accepted international system of units you can use to carry out measurement. There will be trouble. There will be trouble, because this part of the country may produce their own, and if you export it to somewhere else, you notice that what they call kilogram here may be different from what is called kilogram. There will be problem. There will be problem. So measurement is basically a means of communication. It's used by scientists and other scientists, engineers, business traders, and what have you, to do to understand natural phenomena. And it has practical ends, because practically most of the things you say theoretically, you can practicalize them by having proper measurement. Without measurements, there will be would there be titration in your chemistry? There will be no titration in your chemistry. Would there be in physics where you do some experiment about weight? You can't even know which is which. Which weight is which, because there will be confusion everywhere. Now, I don't know if there's any question. Now let's continue. In any measurements, two things are involved. Two things are what? Involved. In any measurement, two things are what? Involved. All these things I've been saying since just preamble. I'm just trying to create a level playing ground for you to understand what measurement, the importance of what measurement. Now we are going deep now. For every measurement, there are two things involved. Number one is the number, and number two is the what? Units. Number one is the what? Number. Either I call it number or quantity. And number two is the what? Units. Either I call it number or I call it what? Quantity. And number two is what? Units. Either I call it number or quantity, and number two is what? Units. Now, and the number or the quantity and the units are normally written what? Together in this form. You see something like this. 20. This is the number. This is the what? Can you see the board? This is the what? Number. Let's say 20 meters. 20 what? Meters. This is the what? Units. Are we together? This is number. This is the unit. If you say you got a measurement without units, it's nonsense. True of us, it doesn't make sense. If you say that have you measured it? Okay, where is the weight? Have you weighed it in? Okay, what is the weight? You say 20. Does it make sense? Does it make sense? Doesn't make sense. So any measurement without unit is useless. Is what? Useless. It's not a measurement. So in a measurement you have numbers and what? Units. That's why in sciences you are doing calculation, and when you get to the answer and you forget to put the unit, you have failed that. Hope you know you have failed it. That's why we are very serious about it, to put your what? Units. To put your what? Because 20 can be what? Anything. 20 is abstract. 20 is what? Abstract. With the units, that 20 has become what is called a denomination, a denominate number. With the unit attached to 20. If you just write 20 without unit, this 20 is just an abstract what? Number. We call it what? Abstract what? Number. We call it abstract. It has no meaning. What is 20? 20 what? But when you put the units, it will become a denominate what? Number. It becomes a denominate what? Number. Denominants. Denominate what? Number. When you put units. So, whatever the quantity or whatever you got from a measurement is a denominate what? Number. Measurement result to a denominate what? Number. In different denomination, depending on the unit. It can be meter, which is for length or distance, as the case may be. It may be in kilometer. It may be in seconds, which is time. It may be in meters. Okay, I've said meter. It may be in kilogram, which is what? Weight or mass. True of us. Good. Even though in physics, weight is not actually kilogram. Weight is what? Newton. Weight is what? Newton. In physics, we are exact about it. We call it mass. Mass is in what? Kilogram, not weight. Weight is in what? Newton. When it comes to physics, we don't joke with that. Now let's continue. Now, what are they? Why do we now carry out measurement? I think I have explained that. Now, what are the qualities or characteristics of the unit of a measurement? Remember, I talked about that a measurement must have a what? Unit. So, what are these features or characteristics of a unit, or what a unit of a measurement must possess before you can say that it is a what unit. You can call it features, you can call it characters, or what makes a unit, what a unit of a number, a unit of a measurement must do what? Possess. The features it must possess for it to be a what? Unit. Remember I missed when I was talking about the imports, the way we measure. I said that to avoid ambiguity, right? Now, here the first feature is that the units of measurement should be possible or easy to define it. It should be easy to be defined unambiguously. It should be easy to be what? Defined unambiguously. It should not lead to what? Ambiguity, confusion. Am I communicating? It shouldn't be ambiguous. If it is meter, it should be what? Meter. That's what it means. So it should not be what? Ambiguous. You should be able to do what? Define it. Then number two is that the unit of measurement should be easily what? Reproducible. It should be easily what? Reproducible. What does this mean? It means that not if you come today and weigh and measure this length in meter, it gives you 20 meter. Tomorrow you see 30 meter. Next tomorrow you see 40 meter. Does it make sense? Is it reproducible? It's not. Am I communicating? So it should be, if you measure it, use another instrument, measure that particular length. If it should be able to give you the same value. That's the meaning. Then another one, of course, being reproducible should help it. Being reproducible should be help you to be constant as you move from place to place. So the third point is that it should not vary. Of course, it should not vary from place to place, or from place to place. Yes, it should not vary. See what I mean? If you have a measurement, maybe you measure it by 2 a.m., it will give you 1 centimeter. If you measure it by 3 p.m., it will change. Or if you measure it here, it will what? 5 p.m. If you measure it here in this class, it's 1 meter. You go to the other class, it changes to what? 2 meter. You shouldn't change from one place, from a particular time to another time, or from one place to another place. It should not change. It should be constant. When I say reproducible, did you understand what I mean by reproducible? I mean that if you use this instrument to check it, it will give you the same thing. I'm not communicating. If you use, okay, this is a ruler, a metric rule that graduated properly in meter or whatever, use it to check a measurement. Take a measurement of a length, it will give you 5 meter or 2 meters. You use another metric rule, calibrated the same way, it should also give you what? The same value. That's the meaning of what? Reproducibility. But the third one is that it should remain constant. I think I've mentioned this third one. It should be constant from where? Place, and from place to place, and from time to time. It should not vary. Now, another feature is that it should be possible to multiply or divide it. Yes. You should be able to do what? Multiply or divide each one of the standard. Let's assume now we have 20 meter. Look up. This unit should allow you to multiply it with 2. True or false? It's not true. It should allow you to be able to do that. This unit meter should be able to allow you to multiply it with what? 2, or to divide it by 5. It should do what? Allow it. If you multiply 20 meter by 2, you get what? 40 meter. So it should be able to allow you to do this multiplication and what? Division. Then if you do 20 meter divided by 5, you have what? 4 meter. So you should be able to do what? Multiply and do what? Divide the units. So let's continue. Any questions so far? Any questions so far? No question. We are entering into the what? Into the what? Measurement. Remember I said that a measurement has quantity or number and their what? Unit. Are we together? Remember I said that a measurement has what? Quantity or number. Use quantity. I think quantity is better. Quantity and what? Units. Quantity and what? Units. So in a classical, you can say that measurement has to do with quantity of substances. True or false? True or false? In measurement, you have to do what? Determining the quantity of what? A substance. It's not true. That's what determines the measurement. That is the reason behind what? Measurement. Either by quantity or extent. Hope you know that there are some you cannot quantify. Can you tell me the quantity of a length? Can you? Is what? It can only be extent. True or false? Quantity or extent of a what? Of a what? Of a what? Substance. Now let's leave it at that. Now let's now start with that quantity. We have quantity here, right? We have what? Quantity here, and we have what? Units. Now let's look at this quantity. Remember, this is measurements. Under measurement, remember, measurements. You have what? Quantity, right? I want to have a table now for you to understand where we are going to now. Under measurements, let me put what we have been doing here in writing. Under measurements, in a tabular form. Under measurements, you have where what? Quantity, right? Quantity and what? Units. Then let us now look at quantities. Under quantity, we have two quantities. We have fundamental what? We have what? Fundamental what? Quantity and what? Derived what? Quantity. We have what? Fundamental and what? Derived what? Quantity. Fundamental quantity and derived what? Quantity. Under unit, you also have what? Fundamental what? Unit and what? Derived what? Derived what? Units. Under measurement, we have fundamental quantity. Under measurement, we have quantity and what? Units. Now, under quantity, we have fundamental quantity and derived what? Quantity. Under unit, we also have fundamental units and derived what? Units. So this will take us to another phase of this lecture. Let us now look at fundamental quantities. What are fundamental quantities? What are fundamental quantities? Any idea? Kamsi, what is a fundamental quantity? What is a fundamental quantity? Kamsi, tell us.
Your quantity, which other quantity depend on? Your quantity, which other quantity depend on?
Quantity, which other quantity depends on? Does a fundamental quantity depend on any quantity? Good. So let's go. So fundamental what? Quantities. So take it down. Fundamental quantities, they are basic quantities. They are basic quantities that are independent of the other quantities. They are basic quantities that are independent of the other quantities. And the other quantities depend on them. Fundamental quantities are basic quantities which are independent of other quantities, and other quantities are dependent on what? Them. What it means is that from fundamental quantities, you can get the other what? Quantity. You can combine one or two fundamental quantities and get the other what? Quantities. Am I communicating? Am I communicating? All right. So, what does this mean? What this means is that other quantities are derived from where? Fundamental quantities. Other quantities are derived from where? Fundamental quantities. Other quantities are derived from fundamental quantities. They depend on fundamental quantities. Now, let's define fundamental unit at the center. Or before we go to fundamental, examples of for fundamental quantity, we have examples of fundamental quantities. We have length. Length is a fundamental quantity. Length is length. There's nothing you can combine to get length. True or false? Length is what? Length. Length is a fundamental quantity. Another fundamental quantity is time. Time is time. There's nothing you can combine again to form what? Time. Time is what? Time. Another fundamental quantity is mass. Mass is mass. There is nothing you can combine to get what? Mass. Mass is mass. It doesn't depend on any other quantity. So mass is mass. Another fundamental quantity is electric currents. Electric currents. Okay, is it like formula for mass? Does mass have a formula? Does mass has a formula? Does it have a formula? Another thing you should know that fundamental quantities have no formula. That's a very important point on how to note fundamental quantity. Fundamental quantity has no what? Formula. So electric current is also a fundamental quantity. Temperature is a fundamental quantity. The amount of a substance is also a fundamental quantity. Amount of a substance is also a fundamental quantity. Amount of a substance is also a fundamental quantity. These are fundamental. You can find out, you can look for more. You can research for more on your own. Other examples of fundamental what? These quantities have no, you cannot say this is the formula for mass, this is the formula for time. No, it doesn't exist. So they are what? Fundamental quantity. What is length? What is a length? If you're asked to define a length, what will you define length as? What is a length? Remember, I talked about extent here, right? A length is what? Extent. Remember, I said that measurement measures what? Measurement takes care of what? Quantity and what? Extent. So, length is defined as the extent of space or distance extended. Length is extent of space. Extent of what? Space. Or what? Distance what? Extended. This is extent of space. This is space now. Look at this place. Here to here is length of space. This is extent of what? Space. It's not true. Is extent of space or what? Distance extended. Distance from here now. From here to what? Here. Is the distance extended. Is length. Am I communicating? Is what? Length. Now, another one is mass. We have defined mass in this class in chemistry. We said that mass is the quantity of what? Matter. In a substance. True or false? True or false? Mass is a quantity of what? Matter. A substance what? Contained. That's the mass of the what? Substance. And we say that mass of a substance is what? Does it change? Does mass of a substance change? Chinwe. Does the mass of a substance change? It doesn't change. It's a constant. Does the weight of a substance change? Good. So mass of a substance doesn't change. It's constant everywhere. Your mass, come see, is your mass everywhere. It doesn't change. So mass of a substance is constant. It doesn't change. It is the quantity of matter contained in a substance. That's the mass. Now, what is time? What is time? What is time? Time can be defined. Time is a quantity in which events are distinguishable with reference to before or after. In a time when in fact, time has to do with interval of occurrence of what? Event gives you what? Time. I'm not getting the difference, the interval between events, between when this event happens, either before this particular standard or after this particular event. This interval in occurrence of event gives you a what? Gives you what is called what? Time. Gives you what is called what? Time. Gives you what is called what? Time. Now let's look at fundamental units. Let's look at fundamental units. What are fundamental units? I want to treat fundamental quantity, fundamental units so I can marry two of them. Are we together? Are we together? Are we together? Are we together? Then I'll treat derived quantity and derived what? Units, so as to marry two of them together. Now let's look at fundamental quantities. Fundamental unit. What are fundamental units? Just the same way we define fundamental quantity. It's simple. Anywhere you see quantity, you put what? Units. Are you together? Go back to what we define as fundamental quantity. Any place you want to define fundamental unit, go to the definition of fundamental quantity, write it again. But any place you see quantity, you put what? Units. True of us, that's give you what? Fundamental what? Units. Instead of saying fundamental unit, for the fundamental quantity is the basic quantity upon other quantities what? Depend, right? Simply say fundamental units are the basic units upon which other units what? Depend. Am I communicating? Fundamental units are those units that are independent of other what? Units. And other units depend on what? Them. Fundamental units are units that are independent of what? Other units. In fact, other units depend what? On them. Other units are derived from fundamental units. Other units are derived from fundamental units. And fundamental units are the units of the fundamental what? Fundamental units are the unit of fundamental what? Fundamental units are the unit of fundamental what? Fundamental units are the unit of fundamental what? Quantities now. It's not true. It's not true. Fundamental units are the unit of fundamental what? Quantities. Fundamental units are the unit of what? Fundamental quantities. Fundamental units are the units of what? Fundamental quantities. Fundamental units are basic units upon which other units depend. They are independent of what? Other units. And other units are derived from what? Them. They are the fundamental units of what? Fundamental quantities. They are the units of what? Fundamental quantities. Now, examples of fundamental units. Just the same way you have fundamental examples of fundamental quantities. Just write out the unit of those quantities. These are the fundamental what? Units. Let's go to a fundamental unit, a fundamental quantity, and its fundamental units. Fundamental quantity like length. Length. The fundamental unit of length is what? Meter. The fundamental unit of length is what? Meter. And the symbol is what? M. And the symbol is what? M. The fundamental unit of length is what? Meter. And the unit is what? M. And the unit is what? M. The next one is what? Time. Next one is what? Time. Time is a fundamental quantity. Then the unit of the fundamental units here is what? Seconds. Seconds is a fundamental unit. Seconds is a fundamental unit because it's the unit of what? Time, which is what? A fundamental quantity. Seconds is a fundamental unit because it's a unit of is the unit of what? Time, which is a fundamental what? Quantity. And the symbol is S. The symbol is what? S, small letter S, as the case may be. Now, the next fundamental unit is what? Kilogram. 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 Kilogram is a fundamental unit because it's a unit of what? A fundamental quantity, which is what? Mass. Kilogram is a fundamental unit because it's a unit of mass, which is a fundamental quantity. Then symbol is what? Kg. The symbol is what? Kg. Now, another fundamental unit is what? Ampere. Another fundamental unit is what? Ampere. Ampere is a fundamental unit because it's a unit of what? Current, electric current, which is a fundamental unit. Ampere, fundamental quantity, Ampere is a fundamental unit because it's a unit of what? Electric current, which is a fundamental quantity. And the symbol is what? A. The symbol is what? Capital A. The symbol is what? Capital A. Ampere is a fundamental unit because it's a unit of what? Electric current, which is a fundamental quantity. And the symbol is what? A, capital A, Ampere. Now the next fundamental unit I want to talk about is Kelvin. 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 This is mass. This is length, time in seconds. This is mass in kilogram. This is electric what? Current in what? Ampere. Electric current is what? The electric current is what? Ampere. Ampere. So the symbol of the unit is what? Capital what? A. Ampere. Now the next one I mentioned temperature, right? Temperature is Kelvin. Temperature is what? Kelvin. The Kelvin is a fundamental unit because it's a unit of what? Temperature, which is a fundamental quantity. And the symbol of the unit is what? K, which is what? Kelvin. Capital what? K. Now, the next one I want to mention here is the next fundamental unit is what? Mole. The next fundamental unit is what? Mole. And mole is the fundamental unit because it is a unit of what? Amount of substance. Amount of substance. Are we together? Amount of substance. And the same, and the abbreviation, you can call the abbreviation or symbol, anyone is okay. For moles is MO, this is moles. Mole. Amount of substance, mole. Amount of substance, sorry, this is amount of substance. What am I saying, sir? Sorry, this is temperature, not Kelvin. Please, here is what? Kelvin is not a fundamental quantity. It's a unit, right? But temperature is a fundamental quantity whose unit is what? Kelvin. Here is mole. There's something I miss. If you go back to the fundamental quantity we listed and write the symbol of those quantities, please. The symbol of length is what? Is what? L. The symbol of length is what? L. The symbol of length is what? L. As a fundamental what? Quantity. The symbol is what? L. The symbol of time is what? T, right? Then the symbol of mass is what? M, right? Capital M. Then the symbol of, as a fundamental quantity, not unit, the symbol of electric current is what? Is what? Is what? Is what? Is what? Electric current. I'm not talking about the unit. I'm talking about the quantity itself. The unit is what? The symbol is what? I. Have you forgotten? Even you. Current. I. You have forgotten. The symbol of the. Please put this thing I'm calling now in the fundamental quantity. Please. Their symbol is very important. The symbol is what? I. Then the symbol of what? Temperature. Please. Time. Don't mistake. Sometimes you see temperature as something like this. Temp. Are we together? To avoid confusing it with what? Time. Are we together? Or you simply make this one small t, but it's better you leave it like this. Leave temperature as temp. Then amount of substance, mole, is n, small n. Small what? N is symbol for what? Mole. Symbol for what? Is it mole? Sorry, mole is a unit. Sorry. Amount of substance is the symbol is number of mole. The symbol is what? Small n. There are other examples you can find out and make up your note with. Now, let's look at derived quantities. Let's look at derived quantities. Let's look at derived quantities. What are derived quantities? What are derived quantities? What are derived quantities? What are derived quantities? Any idea? Any idea? Of course, we agree that derived quantities are gotten from where? Fundamental what? Quantities. Derived quantities are gotten from where? Fundamental what? Quantities. Derived quantities are gotten from where? Fundamental quantities. You get derived quantities from where? Fundamental quantities. Now, what are derived quantities? Derived quantities are those quantities that you obtain by simple combination of what? One, two or more fundamental quantities. Simple. Derived quantities are those quantities you obtain by simple combination of two or more fundamental quantities. Derived quantities are those quantities that are obtained by simple combination of two or more fundamental quantities. Good. Derived quantities have you seen how derived quantities depend on fundamental quantities? Have you seen it? Good. Derived quantities depend on what? Fundamental quantities. Derived quantities depend on what? Fundamental quantities. Derived quantities depend on what? Fundamental quantities. Now, next thing I want to talk about is what? Examples of what? Derived quantities. Examples of the what? Derived quantities. Examples is area. Do you know, can someone explain to me why area is a derived quantity? Can someone explain to me why area is a derived quantity? I'm waiting. Can someone explain to me why area is? What is the area of a substance? What's area? Talk now. Have you seen that length times what width? They are combining the same fundamental. What is the fundamental? Width and length, are they the same quantity? Width and length. Length times width. They are both measure of what? They both measure distance, true or false? Or length. It's not true. Forget that they gave it width a different name to tell you the dimension is measuring, but it's the same what? They have the same unit, which is meter. They talk about the same measure of what? Distance or what have you. But they have different names to tell you dimension they are going, but they have the same what? Units. So have you seen how they combine length and width to get what? Area. Have you seen that area is a what? Derived quantity. So area is a what? What of volume? What does volume combine? Length and what again? Breadth and what again? Height. Both height both breadth both length they are measure of what? Distance or length, as case may be. They talk about the same thing, but the dimension. Height talks about vertical like this. Look at height, talks about like this. But it's also in what? The same unit with what? Length. Length is like this. True or false? Then breadth talk about the thickness. True or false? So they all talk about what? Measure. They are all measure of what? That's why they have the same unit. That's why the unit of volume is m what? Meter what? Cube or centimeter cube, because you multiply the three lengths. They are three of them are lengths. True or false? So have you seen how we derived volume from what? The same what? From say what? Length. So volume is a what? Derived quantity. Remember I told you that, please put in when you explain derived quantity, that derived quantity also have what? Formula. Unlike fundamental quantities, derived quantities have what? Formula. True or false? Does area have formula? Does volume has formula? Because they are what? Derived quantity. A very important point you should know that derived quantity have what? Formula. But the fundamental quantity don't have what? Formula. Fundamental quantities, they don't have what? Formula. But derived quantities, they have what? Formula. This is a very important point you should note. Very, very important. That's why area has formula. Length times what? And that's why volume has formula. Length times width times. Are we together? Now let's look at density. Does density has formula? So is density a derived quantity or fundamental quantity? Chinwe. Is density a derived quantity or fundamental quantity? Speak out. It's a derived quantity, but because it has what? Formula. What is the formula for density? Have you done density in your class? So what's the formula for density? Amber. Density is mass over what? Volume. If you watch now, watch. Let me tell you how density was derived. Watch. Mass is a fundamental quantity. Mass is fundamental, but over volume. Look at volume. Volume is a derived quantity. Volume came from 3 lengths up here. Length into what? 3. Have you not seen you combine length into 3? Use it to divide mass before you derive what? Density. So density has one fundamental quantity and one derived quantity because volume is a derived what? Quantity. Is it making sense? So density is a derived what? Quantity. It has what? Formula. Velocity income. Is velocity a derived quantity? Velocity is a derived quantity. You know why velocity is a derived quantity? What is the formula for velocity? What is the formula for velocity? Good. Distance over what? Time. Please. Anyway, we'll still do it, but you define speed. Distance has no direction. It's a scalar what? Quantity. But velocity is a what? Is a vector quantity. It has direction. So velocity is displacement over what? Time. Velocity is what? Displacement over time. Have you not seen? But displacement is also a measure of length. Are you aware? Because displacement is a measure of what? Length. Displacement is also a what? Length. So the velocity is certain as saying length divided by what? Time. True or false? Velocity is certain as saying length divided by what? Time. So velocity is derived from length and what? Time. Is length a fundamental quantity? Is time a fundamental quantity? So displacement was derived from 2 fundamental quantities. Length and what? Time. Length and what? Time. Is it one notebook that you use it for all your subjects? Please do. Keep your note well. Arrange your note well. Don't mix up things. It's not good. Are we together? Now let's continue. Now another derived quantity is what? Acceleration. Who can define acceleration for us? Define acceleration. Define acceleration. Chinwendo. Define acceleration for us. Speak out. We are listening. Define acceleration for us. Come see. Define acceleration for us. Did people do acceleration in your class? You forgotten it? Hey. Okay, acceleration is what? Change in velocity over time. Change in what? Velocity over time. Now, whether it's change or change, no change down. Velocity is still what? Velocity is still what? There. It's simply velocity over what? Time. Is velocity a derived quantity, Chinwe? Is velocity a derived quantity? Yes. Is time a derived quantity? Have you not seen that? Have you not? This is why acceleration is a derived quantity, because it's derived from what? Velocity, which is also a derived quantity, and what? Time. It's derived from what? Velocity and what? Time. It's derived from where? Velocity and what? Time. It's derived from where? Velocity and what? Time. Acceleration is derived from where? Velocity and what? Time. Now, we'll still do derived unit of all this, but I want to break it down small so it can flow. Another derived quantity I want us to look at is force. Force. What is the formula for force? Force has a formula because it's a derived what? Quantity. Oh yeah. Who can tell us the formula for force? Chinwaya. What is the formula for force? Is what? No. Velocity over time talks about acceleration. I mean force. Can you see? Good. Force is mass times what? Acceleration. Force is mass times what? Acceleration. So F is equal to ma, right? Ma. Force is mass times what? Acceleration. Have you noticed something? Let's break down this formula for force. Let's break down this formula for force. I think it's better I'll be writing it on the board. Force. Let's break down this formula for force. Let's break down this formula for force. Let's break down this formula for force. Force is what? Mass times what? Acceleration, right? M is mass, A is what? Acceleration. Is mass a derived quantity? Chinwe, what is it? Mass is a fundamental what? Quantity. What of acceleration? Acceleration is derived from, acceleration is what? Velocity over what? Time. So acceleration is velocity over what? Time. Is time a fundamental quantity? We are breaking down the formula to all. We want to split force down to all the fundamental quantity in force. I think that will help us to understand this thing. Each unit each quantity we bring, we break it down to all the fundamental what? Quantity it contains. Let's do it for better understanding. Let's do it for a better what? Understanding. Look at force. Let's break down force. Force is what? Acceleration. Mass times what? Acceleration, right? Mass is fundamental. True of us is fundamental. But acceleration, is it a fundamental quantity? Derived quantity. So let's break down acceleration and see what will happen. Acceleration is velocity over what? Time. Is time a fundamental quantity? Time. Yes. So we have fund here, right? Any fundamental, I'll put fund there. Is velocity a fundamental quantity? So let's break down velocity to what? Displacement, which is length. Okay, length L over what? time, which is what? T. Is length a fundamental quantity? Length is time a fundamental quantity? Have you seen how we splitted first to go down to the what? All the fundamental quantity that you see in force. So in force, you have mass in force is how many? 1, right? Time is how many? 1, 2. So T times T. So mass is only 1, right? Time is 2. T times T, which is T what? Squared. We have T squared. Length is how many? 1. We have L. Have you seen how we split that force? Force is M, capital M, T squared, and L. This is how we bring down force to all the fundamental what? Quantities. Does it make sense to you now? This is what derived quantities are about. But we still talk about this when we go after this one. We discuss what is called dimension. It's dimension that I will open. We discuss this one more. Are you okay? Now let's pick another derived quantity. In fact, let's do it well. Area. Area is what? Area is what? Length times what? Width, right? Both length and width are measure of length. True of what? They have the same measure. So we have what? L times what? L. So area is what? L squared. So this is dimension of what? Area. So area is a derived quantity. Now another one is, let's look at volume. Volume is length times what? Width times what? Height. Is it width or breadth? Anyone? Times what? Height. All these three are what? Measure of length. They are all what? L. Are you following me? Are you sure? So we have L times what? L times what? L, which is what? L what? Q. So this is dimension. This is the what? What make up what? Volume. So volume is a derived quantity. We have done that of what? Force. Yeah? And got this. This is for what? Volume. This is for what? Area, L square. Area is L square. Volume is L cube. Then force is what? MT square L. Now let's pick another one. Velocity. Let's look at velocity. Velocity is what? Displacement, right? Velocity is what? Displacement over what? You're not listening to this I'm doing. Hey, okay now. You're not listening to this. People are funny. Yeah. Oh. Velocity. Velocity is what? Okay, let me give you like 1 minute to finish. So we can. I'll do that of velocity. Okay, now let's look at what? Let's look at what? Velocity is what? Displacement, right? Displacement over what? Time. Is displacement, is it a derived quantity or a fundamental quantity? Displacement, is it a derived quantity or a fundamental quantity? Fundamental because it's length, true of course. So that means velocity is what? Sorry. First, show you that this is over T. Remember your law of indices. This should be L raised to power minus what? 1. Please. First is MT square. L raised to power minus what? Sorry. ML, sorry. What am I doing myself? This is wrong, please. Let me do it well. Let me do this. Okay, let me finish velocity, then I'll come to force. That thing I did in force is wrong. It's now I just look at it very well. It's wrong, please. Let me conclude with velocity, then I'll come to force. Now, displacement over what? Time. If you bring it down, this is length, right? L. And this is what? Time. Which is what? T. Is it clear? L over what? T. We have brought it down to all the fundamental unit there. Have you seen it? So that means velocity is what? L T what? T what? Raised power what? Minus 1. This is dimension for what? Velocity. L T raised power minus. We are entering dimension. Hope you know. I'm from derived quantity. I'm entering dimension. Is it clear? Now, force. Force. Let me write out force. I don't understand. This one. It's not writing well. This one writing well. Okay. Okay. Let's look at force, okay? Force. Force is what? Mass times what? Acceleration. Mass is already a what? Fundamental quantity, so we leave it at M. Acceleration is what? The formula is what? Velocity over what? Over what? Time. There's only time here, right? So we leave time as what? T. So we have what? Velocity. We have velocity is what? Displacement, right? Displacement over time, right? Over what? This time. True of us. If you bring out this time, it becomes time squared. Oh yeah, it's not true. Are you following? If you bring up this time, it becomes time what? Over time squared. So we now have that acceleration is what? Displacement over what? Time what? Squared, right? So let's move this to their symbol. The symbol of displacement is as a fundamental quantity is what? L. So this is what? L. L over what? T what? Squared, right? This is written as saying L T raised power minus what? 2. This is what? Acceleration. And this is what? Mass. So force is M times acceleration, which is L T raised power minus what? 2. So force is now what? ML T raised power minus 2. This is it for force. Is it clear? Is it clear? Is it clear? That's dimension for what? Force. That's dimension for what? Force. Have you seen how we move from derived quantity to what? Dimension. I don't want to mention units. When we are done with this, I will just mention, I just tell you their units, simple. But just know, I want you to know how to do it directly from their what. Sometimes they may give you a unit in question and tell you to find the dimension of that unit. Maybe I will look for a jam question or word question where they ask this question and give you to solve. I think that's what I will do for understanding. Are we together? Good. Are you tired? Child, stand up and go and walk around. You are tired too? I look at this one, you came from home. Whatever. But it's okay. Now let's look for another derived quantity we have worked on. Let's look at density. Let's work on density. And let's see what we get from density. Can I clean? Let's look at density and see what we get. Let's look at density and see what we get. For density, you have something like this. What is the formula for density? This is what? Mass over what? Volume. So you will agree with me that density is a derived quantity. Mass itself is already a fundamental quantity, right? So we leave it as we write the symbol, which is what? M. But volume is what? Length times what? Times what? Which is same as saying capital M over what? L times what? Times what? Anyone, whether width or breadth, anyone is okay. Whether width or breadth, it's okay. Breadth, oh yeah. So what does it mean? L times what? Bring it out to the symbol now. We are done with this now. What is breadth? Is it a measure of length? Yes. Height is a measure of length. Distance, which is L. It's not L. And so L times what? Times what? Are you following? So we have what? M over what? L what? Cube. Is it clear? So bring it indices. Bring it out to be in linear form. You have what? L what? Good. So density. Density is what? ML T raised power minus what? 3. This is dimension of what? Density. Is it clear? Huh? How did I get what? Hey, sorry. My brain is firing. Time has no business here. It should be L raised power what? See what I wrote to say. I came here and wrote L T. Thank you. Let me see what you wrote. Isumde? Asalom Isumde. So it should be what? ML raised power minus what? 3. That is dimension for what? Density. Dimension of what? Density. Let me look for another quantity here. Let's look at energy. Energy or work. Are we together? Energy or work. Any of them, they have the same unit, okay? The same formula. We have not, let's look at energy or work. What is work? Who can define work for us? Please, anyone I wrote, any derived quantity I write there, make sure you know the formula. Hope you're better their formulas. Are you sure? Good. Now let's look at work. Either you call it work or what? Anyone? Or what? Energy. Let's see. What is work in physics? I define work for us. Work is what? Formula for work is what? Or work is what?
100 divided by work.
Come see, your work is what? Work is what? Force times what? Good. Work is force times what? Distance. Work done is what? Force times what? Actually, it should be work. It should be work time. Work should be force times displacement, or force times distance in the direction of the what? Force. Either you say work force times distance, or you say force times either you say force times displacement, or you say force times distance in the direction of the what? Force. Are we together? So if you use distance, always put direction there. Force is work is force times distance in the direction of the what? Force. Or simply say force times what? Displacement. Any of them is okay. Now look at this now. Let's break this formula down. Remember, we have broken down force here, somewhere here. Distance, is it fundamental? So this one is simply what? What? Huh? Huh? Which is what? Symbol now, symbol. L. Is what L? Let's break down force. Force, remember force is mass times what? We have done that, right? Can we just put it here or do we break it down from the beginning again? Should we break it down? Do you understand how you broke it down? So what did we get here? M what? M what? LT. Are you sure? Raised to power what? Minus 2. MLT raised to power what? Minus 2. This is force. MLT raised to power minus what? 2. MLT raised to power minus 2. So what do we now do? We multiply them. Remember this multiplication. There's multiplication here, right? We multiply them. So what will be the answer? Tell me the answer. MLT raised to power minus 2 times L. What will be the answer? M. Good. The law of indices is here. Have you seen why we did law of indices? Okay, sorry. 8 power minus 2. Have you seen why we did law of what? Indices. Is it helping you here now? Is it? So ML square T raised to power minus what? 2. This is what? Energy. This is dimension for what? Work / what? Energy. Let's look at now. Let's look at power. Let's look at power. Let's look at power. Let's look at power. Let's look at what? Power. What is power? Formula for power is what? Formula for power is what? Oh, yeah, power is what? Define power for a formula. What is formula for power? Oh, yeah. Power is what? No idea. Oh, yeah. Can we see? Power is what? You've forgotten it. Power is work over what? Time. Work done over what? Time. Or simply say work over what? Time. Power is what? Work over what? Time. So if you want to blow grammar, you can say that power is a time rate of doing work. The rate at which you do a work is what? Power. Is it clear? How fast you do the work. Now, so power is work over what? Time. Now look at this thing. Have you done work before? Is work a derived quantity? Is work a derived quantity? What are you saying? Is work a derived quantity? I say, remember, you know, here. What you just did now? Yes. Hey, work is a derived quantity. So time, is it derived or fundamental? So we don't have any issue. We have already known time to be what? Fundamental, which is what? Speak out. T, good. What of work? Do we break down what work in, or do we use the one we did before? Can you do it on your own? That's the question. Can you do it on your own? Okay, so what do we got? What do we get in work? M what? ML squared. T raised to power what? Minus 2. This is the formula. This is the dimension for this. But I want it to be in linear form. So how do we make it to be in linear form? If we make it to be in linear form, what will be the answer? The power is what? Oh, yeah. Law of indices is here. We did this in. M what? M L square. Good. I like that. 3 raised to the power minus 3. This is dimension of what? Power. Have you seen why power is a derived quantity? Power is a derived quantity. Power is a derived quantity. Let's look at another one. Let's look at momentum. Let's look at momentum. Let's look at momentum. What's a formula for momentum? No idea. Hey, momentum, What are you doing? Open that book. What are you hearing you? Come see you. Okay, I thought you were peeping to tell me the answer. Oh yeah, what is momentum? Oh yeah. Mass time what? Volume. Where? Can you say it in Agam? It's not volume, please. Momentum is mass times what? Velocity. Momentum is what? Mass times velocity. Momentum is mass times velocity. Momentum is mass times velocity. Momentum is mass times velocity. Now let's break it down. Let's see what we get. We already know mass, right? Is mass a fundamental or derived quantity? So what do we have here? Capital what? M. Times velocity. Do we break down velocity again, or do we use the one we have done before? So what do we get in velocity? M. Are you sure? Is it true? Come see. M what? M what? Raised to power minus 1. So if you multiply M. There's no M. Okay, so, sorry, there's no M. There's no mass in velocity. Sorry. It's L to raised to power minus 1. So that means momentum is what? Momentum is M L to raised to power what? Minus 1. So momentum is what? Momentum is what? M L T raised to power what? Minus 1. M L T raised to power what? This is momentum. Momentum is what? M L T raised to power minus 1. Now let's look for another derived quantity. Maybe after this one we'll stop. We'll go to the units and they conclude there. Pressure. Let's look at pressure. Pressure. What is the formula for pressure? Pressure is a derived quantity. What is the formula for pressure? Remember, derived quantities have formula. But fundamental quantities, they don't have a formula. Actually, what's the formula for pressure? Answer now. If you don't know, you say you don't know it. No idea. Chiwa doesn't know it. Come see. Pressure is what?
Force over time.
Force over time? No. You don't know. Pressure is force acting per unit area. So pressure is what? Force over what? Area. Write it down. Pressure is what? Force over what? Over what? Area. Pressure is what? Force over what? Area. Pressure is what? Force over what? Area. Now let's break this thing down. Can you remember that have we worked on force before? So what did we get in force? M what? Speak out now. Speak out. Sit up. You're in class. Speak out. M what? Force is ML 3 raised power minus what? 2. So we put it in the what? Numerator. We have what? M what? L T what? Raised power what? Minus 2. All over. Area is what? L what? Squared. Area is what? L squared. So that means pressure is what? Use law of indices to tell me what pressure is. Therefore, pressure is what? Tell me fast. No time. Pressure is what? M what? L. This is 2. How? How is it monastery? Check well. Look, go to your law of indices again, please. Oh, yeah, now. How? Division. What are you saying? If L in the numerator cancel L in the denominator, will L remain in the denominator? How many L will remain in the denominator? So put it in linear form. It becomes what? What are you saying here, sis? L is for minus what? 1. Then T what? So this is the what? Dimension for what? Pressure. Dimension for what? Pressure. Any question? You can find out more other examples on your own. I've dismantled up to 6 derived quantities, right? Now, those derived quantities we have dismantled, I want to talk about their units. After that, we end this class. Let's talk about their units. Let's go to now derived what? Units. Derived what? What are derived units? We have discussed derived quantity. Derived quantity is what? Define derived quantity for us from what we define. What is it? Increase the volume. They are what? They are what?
Obtained by simple combination of 2 or more.
They are obtained by what? Combination of what? Fundamental quantities. Know that fundamental quantity may be the same fundamental quantity or different. I hope you know. Are you aware that it may be the same fundamental quantity or more? Hope you know. I'm not complete because something like length, something like volume. Volume has the same fundamental quantity, right? Which is what? Length into 3 times. It's not 2. Area has the same length into how many times? 2. So it may be the same fundamental quantity that may combine 3 times or 2 times, depending. Now, the next one is what? So if we are able to define derived quantity as what? Quantity obtained by what? Combination of what? Simple combination of what? 2 or more what? Fundamental quantity. So that means derived units are units obtained by what? Simple combination of 1, 2 or more fundamental what? Units. Simple. It's just the same thing, but whenever you see quantity, you put what? You put what? Units. Simple. Whenever you see quantity, you put what? Unit. Wherever you see quantity, you put what? Units. Now let's look at this. Let's see those things we have called. Let's look at their units. So from this thing we have said so far, what do you think is the unit of area? First of all, you ask yourself, what is the fundamental quantities in what? Remember we broke this in. Sit up. That's not how to stay in class. Sit up. If that thing is too far, look for one that is closer. You can come here. Now, that's why we say that that's why I have a reason for breaking this thing down like this. I broke it down like this. Let's look at area. We say that area is what? Length times blah, 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 blah. Length times width, right? Now, what are the fundamental quantities in that? Length into how many times? 2. And what is the fundamental unit of length? Meter. We say it here now. Meter, right? So, what do you now think will be the fundamental derived unit of area? Meter times what? Meter. Which is meter what? Have you not seen where they derived m squared as the what? As a unit of what? Of what? Area. Is it clear? Is it clear? Is it clear? Good. So it's because we say that we got the fundamental dimension of area to be L what? This is the fundamental unit, fundamental quantity. What is the unit of this fundamental? Just if you want to know the unit, just go to the dimension and get the unit. Is it clear? This dimension L what squared, is not true. What is the unit of this L? Meter. Just replace L with what? Meter. L is what? Meter, right? Just replace L with meter and you get the SI unit of what? The unit of what? Which is now what? So area is what? M what? Square. Area is this by dimension. L is M. So area is M what? Square. Is it clear? It's simple. This is how to get the derived what? Units. Now let's go to volume. What is the dimension of volume? Volume is what? Go to what we did. L what? L cube, right? L cube. So if volume is L cube, remember that this L, the unit is what? M, right? Meter. That means that therefore, the SI unit of volume is what? Replace L with a meter what? Is it clear? You may have centimeter cube. You may have, but the SI unit is what? Meter cube. Is it clear? Good. Now let's look for another one. Density. Density. What do we break down that dimension for density? M what? L. Raised to power minus what? Good. M L raised to power minus. This M is fundamental mass, which is for fundamental unit, right? What is the fundamental? What is the unit of mass? I'm asking you. Well, what is the unit of mass? Kilogram. Good. So the symbol is what? Kg. So we have what? Kg, right? Times this L. L is for length. What is the What is the unit of length? M what? So the SI unit for this is kilogram what? Per meter what? Cube. Hello? Are you together? But sometimes, the one they normally use is that sometimes you see, most time you see the kilogram in what? Gram. Are we together? You see this in cm. Gram per what? Cm cube. Have you seen this like this before? It's again. Yeah, you are not seeing this like this before. So what this did you do for what are you even saying? There are different volumes. We have volume in meter cube. We have volume in cm cube. We have volume in dm cube. These things are different units. But the SI unit we are using here is kilogram per meter what? Cube. So this is the what? Are you okay? Are you okay? Are you following? Sit up now. Sit up. I don't ever say sit there. If you're tired, stand up and go around. Don't sit like that in my class. If you're tired, stand up and go around while you are still listening to class. That's how to do it, okay? This is laziness. It's not good. Now, it can be kilogram per meter cube, or you see gram per cm cube, or sometimes you may even see gram per dm cube. You may see gram per what? Per what? Dm cube. Or you may see like this. Or gram like this, cm cube. Or kilogram per what? Is it clear? That's density. Let's look at as an velocity. Let's look at what? Velocity. What is the dimension for velocity we derive here? Velocity is the dimension we got is what? L what? T raised to power minus what? 1. Look at it. So this is L. What is the unit of L? L. What is the unit of L? Yeah. What is the unit of L? What's going on here? Meter now. It's not meter. Are you tired? What's going on? This is what? Meter. Good. This is what you've been shouting here since for the past 2 hours. You're looking at me as if we are lost. L is what? Meter. This is T, which is what? Time, right? Time is what? Is what? Hey, what's going on here? Look at your book now. What's happening here? Here. Is what? S, right? So this is S raised to power what? -1. Have you now seen where is it that the SI unit of velocity is what? Meter per second. This is where how it is derived. Meter per what? Sometimes you see it like this. Or you see it like this. Meter slash what? Seconds. So the SI unit of velocity is what? Meter per second. So it's a derived what? Unit. It's a derived what? Units. Please, in class, don't get absent-minded. This thing I'm seeing now is a result of absent-mindedness. What I'm saying for the past 2 hours, not just like making now, is that you didn't understand it, but you say you understood it. So what's the problem? Or you are absent-minded? It will be 2 of them. Now let's conclude before we go. Let's look at now and let's look at call all those derived quantities. Let's trash their units. Let's try the unit one after them. Call those from fast. Let me fast now, please. Next one is what? Force. What do we get as force? The dimension is what? L what? Which one what? Minus what? 2. So M is what? Unit of M is what? kg. M is what? Seconds what? So actually the unit of force is kilogram meter per second what? Squared. But because of the work of Isaac Newton, they call it what? Newton. But this is the actual unit. But they call it what? New what? 10. In what? N. They call it Newton. But this is what it actually, this is what it is. But they call it what? Newton. But this is what it is. Now let's look at, call me another one. Is it clear? Energy or work, right? Let's go. Energy or work, let's use work. What is the dimension? M, L, T is for what? Are you sure? Is it what we have? ML squared T is for 1 as 2. M is what? Kilogram times L is what? Meter. So we have meter what? Squared times seconds. Seconds is 4 minus 2. So this is that as saying kilogram meter square per second square. This look up. This is actually the main unit of what? Work and energy. But because of the work of Joule, the scientist, Joule is a name of a person. Joule. That's the name of scientists that work extensively on this. They gave you that name. Is it clear? Just the same way they gave this one Newton because of his work on force. But actually, it should be what? Kilogram meter per second square. The same thing. Work is kilogram meter squared per second square. But they name it what? Joule. This is name of the scientist. But it's in what? The symbol is J. That's why they'll tell you that work is Joule. It's in Joule. Joule or energy. Have you come across it before? Good. Now let's go to the next derived quantity. Call it power. Let's look at power. Let's look at power. So power, I call it dimension of power. M L what squared? Minus what? 3. 3 is power minus 3. This is dimension for what? Power. Now let's change it to units. What is unit of M? Kilogram times L is what? Meter square times T is what? Second raised power minus 3 per second cube, right? So actually, this thing for power, unit for power is should be what? Kilogram. Are you looking up? Meter squared per second what? Cube. This is what is big. But because of the work of watts, a man named what? Watts. Because of his work, they now give the SI unit of power to be what? Watts. So that's why you see power to be what? In what? Watts. The symbol is what? W. Is it clear? This is actually what it is. This is the derived what? Is there the one we are missing from the one we did before? Pressure encore. Pressure, you're not even done momentum self. Go to the board and do momentum for us. Come in the momentum for us. Fast. Go to the board and do momentum for us. Fast. Don't waste time. Go there fast. Go there and do momentum for us. Get in the board and do momentum for us. Yeah.
This one is minus.
Uh-huh. Good. Kilogram meter per second. Mass times velocity. This is the unit for what? Momentum. Kilogram meter per second. Oh yeah, come and do first pressure for us, human. Fast, fast. Come and do pressure for us, fast. Oh yeah, do pressure for us. Uh-huh. Force over area. Is it?
Minus, this one minus 2.
Okay. So pressure is what? Pressure is what? Kilogram per what? Kilogram per what? Meter. Kilogram per meter per second what? Square. Kilogram per meter per what? Second square. Kilogram per meter per what? Second square. Or simply Newton per meter square. You can break this down to Newton. Watch. You can break it down to force. You can separate this now and you have force. Force is what? What do you get at force? Force is mass times acceleration, right? Force is kilogram. Look up. Force is kilogram meter per what? Per second what? Square, right? This is force. Divided times what? Meter per second. So per meter square. I am aware that this can be taken as this. Kilogram meter per second square over what? Do you agree with me? Do you agree with me? Huh? Where it came from? I separated this. This times this is what? This is 1. 1 minus 2 is what? Minus 1. I know that this is certain as this thing. So that means here is what? Area, right? Or simply meter square, sorry. Meter square. Where this one is what? This is formula for what? This is the unit for what? Force. Which we call Newton, right? Which we call what? Newton. So for pressure, it's either it is kilogram. Note this thing. Newton for pressure. It's either it's kilogram per meter per second square, or simply Newton per meter square, or simply what? Pascal. Any of them is okay. Kilogram per meter per second square, or simply Newton per meter square, or Pascal. This is pressure. Just as we have watt and joule, here we have Pascal. The symbol is what? PA. The symbol is what? PA. Any question? Any question? In the absence of any question, I want to thank us for today. Thank you very much for coming around, and see you tomorrow. Assignments. Let me look for assignment and give you. Don't worry, I'll send it on WhatsApp. Or let me see if I can see any here. Fast. No time. Let me see if I can see any. If I don't see any here, then I'll give you. We'll see in. I'll send the assignment on WhatsApp if I'm not able to see any here. Don't worry. I'll send the assignment on WhatsApp. All right, see you tomorrow. God bless you.